So, time to finish up chapter 24. This video will be sections 3 and 4 because they're fairly short and I can get them both in the same video. So, last time we talked about how gravity warps space-time. The fabric of space gets warped by large masses. It's really cool. So this time we're going to talk about some of the ways that we test general relativity by looking at the motion of Mercury around the sun and light rays being bent by massive objects. So planets precess. This, as we look at this diagram, the orbit around the sun moves slightly from one orbit to the next. All planets precess, and this is because of the pull from other planets. We have the sun pulling on our little planet that's orbiting the sun, but all the other planets are pulling too, and so their combined mass causes a planet to move just slightly. Well, Mercury's wobble is bigger, its precession is bigger than it should be just based on the other planets. And this is because the sun pulls on it more than any other planet. Why? Well, because it's closer to the sun than any other planet. Makes sense. And then light gets curved as it passes massive objects. So we talked about how the fabric of space gets bent. We're going to actually, when we talk about black holes in the next section, talk about how light rays get bent along with that fabric of space. But we have the sun and the light ray coming in from the star, and so it gets bent and comes in towards us. The light from this star should have, been along this line. And so when we look at the star, we look out this way and we assume that the star is out here, but it isn't. Think about the last time you went fishing or you went somewhere where you were looking into water at minnows. Not everybody fishes. I don't. It's boring. Anyway, when you are looking into the water at that fish, the fish is not at the location that you think it is. As light passes from water into air, water and air are two different densities, so the light ray gets bent, Snell's law. So similar to that, it's not the same, but it's similar. That's a good, model. Remember, models are where we use one thing to represent something else. So the fact that that fish is not in the location that it looks like it should be can remind us about the fact that the light from a star gets bent by large gravitational masses. If we are standing on the surface of a star with a flashlight, this is of course assuming that you could stand there without being fried to a crisp, but you stand there and the light from the flashlight goes up. And if we decrease the diameter of that star, remember when we shrink a star, we're actually increasing its gravity. So we shrink it, and those light waves begin to instead arc back down and come back down to the star. We shrink that star enough and all light rays come back down. So no light escapes, and guess what? We've just created a black hole. So how does Einsteinian gravity slow clocks and decrease a light wave's frequency? So we need to stop and remember a couple of things. Nothing can travel faster than light. Nothing. If you observe an object moving close to the speed of light, time for it will slow down. Its length will squish compared to in the direction of motion. I mean, this makes sense. You take a marshmallow and you move it really fast and it's going to smoosh. So compared to the speed of light, we are all smooshy. And the mass increases. And then we always have to remember that, whether or not two objects are simultaneous depends on perspective. Everything in space-time and gravitation, we must remember perspective. Okay, so time dilation formula. Time will appear to pass more slowly in objects based on the speed of the object. So as we get, at speeds that we experience right in here, a fraction of the speed of light, then time occurs basically normal. So, time 1 second takes 1 second. As we move closer to the speed of light, at half the speed of light, 1 second will take, nearly a second, 9/10ish. But if we move up here to 9/10 of the speed of light, 1 second will take less than half a second. At 99% of the speed of light, 1 second has been significantly reduced. So as we get close to the speed of light, objects that are moving close to the speed of light, time nearly stops for them. So if we, got in a spaceship and, with a clock, and we had one spaceship orbiting the event horizon of a black hole out at, a nice safe distance, and one spaceship that got very close, and you set the timer, 50 minutes later for the spaceship that was far away, the spaceship that came in very close, only 15 minutes will have occurred. So most of you have at least heard of the movie Interstellar. They do a really good job of portraying this when the crew goes down to the water planet, and for them they're gone like 7 hours, and for the guy up in the spacecraft far away it was like 14 years. So that will happen. The distance to Vega, 25 light years. If we could travel to Vega and back at 0.999% of the speed of light, for the person in the spacecraft, time will basically not have passed. So you will travel to Vega and back. For people on Earth, 50 years would have passed. And for you in the spacecraft, it would have felt nearly instantaneous. So interesting weirdnesses when we start talking about time travel or faster than light travel. So next section we're going to talk about how all of this leads to black holes.